In the previous lecture, we had discussed about the concept of the center of mass for the system of particles. In this lecture, we will try to review the uh, dynamics, the translational dynamics of the system of particles, which we had considered previously. Let's formulate the equation of motion for the ith particle and apply the Newton's second law of motion to it. So here we have the rate of change of the linear momentum of the ith particle being caused by the external force acting on the ith particle and the summation of all the internal forces due to the other particles in the system acting on the ith particle. So this was the equation for the ith particle. Let us sum up all the equations for all the particles in the system. So that would appear like this. The summation of the rate of change of the linear momenta of all the particles will be equal to the summation of all the external forces. We are just putting a summation sign here, and a double summation appears here. Now we will elaborate this linear momentum. Linear momentum can be written as mi multiplied by the velocity, the mass of the ith particle multiplied by its velocity. The right hand side is the same. And here we see that this term on the right hand side, it becomes a zero vector. Now why does this happen? This term here represents the fact that it's a summation of all the internal forces acting on the system. And you can see that for every force, for every ith particle which is receiving a force from the jth particle, there is also the jth particle which is receiving equal and opposite force from the ith particle, and the line of actions is the same, and so this resultant has to be equal to 0, a zero vector. So if we rearrange this equation, we get the left hand side, which is the rate of change of the summation of the linear momenta for all the particles, and that can be written like this. So here in this previous step, what we have done is we have brought this derivative term, derivative outside the summation, because it's not affected by the summation sign. And we have said that here you have, we know that the summation mi ri dot is the same as if the whole system is moving with the velocity of the center of mass. So the rate of change of mb multiplied by its velocity. So we can write the total effect of application of Newton's second law to the system of particles as the rate of change of the mass of the entire system. The particles may be moving anyway as they like. So here so far we have not imposed any constraint on these particles. The rate of change of the momentum of the whole system, as if all the mass of the system is concentrated at the center of mass and moving with the velocity r dot c with respect to 0 in the frame 0. So this linear momentum is, the rate of change of this linear momentum is caused by the resultant of all the external forces acting on this system. And you can see here that the internal forces are not appearing in this expression.